So let's now discuss about the impulse turbines. Okay, one of the example. So first let's see what is the function of turbines. So turbine, just like pumps they work in the reverse way. Turbines are the energy producing devices. So these turbines are the ones which produce energy and at the expense of the fluid energy. The expense of fluid energy. So if you have a flow like this, and so if I happen to draw a turbine, so this is, let's say, the fluid in. I'm just drawing a schema, just a very simple representation. This is fluid out. This is the energy of the fluid in. This is the energy of the fluid out, and this is the work. So energy out is less than energy in, and the difference is what is this is the work done by the turbine. So okay, so now let's see a very important impulse turbine called the Pelton wheel type. Okay, so this Pelton wheel, well, you have let's say a reservoir somewhere at the higher level, and the turbine setup is somewhere at the bottom. So you have all these penstock, which are the pipes that carry the fluid from higher reservoir to the place where turbines are installed. So this is penstock, or basically the pipes which carry the fluid. Mostly constant dia, can be different dias also. So at here at the exit you have a nozzle. So let me draw it here. You have a nozzle, okay, and before this, if I happen to draw a reservoir like this is the head. Okay, so let's say the total height from the nozzle level to the water level is h, and so this is point number 1, this is point number 2 where it enters, and then you have the Pelton wheel where you have a very larger dia, and then they are kind of buckets which are mounted on the Pelton wheel. Okay, so when the flow enters, it enters with velocity and strikes one of the bucket, and then that momentum of the fluid that drives the Pelton wheel, okay, and provides the necessary torque, and then this is connected to your generator which produces electricity. So this is what happens in a hydroelectric power generation. Okay, so there are two things here. First is the head the head of the fluid that is entering the nozzle. Let's say the energy head is h here and the velocity is v. The entire thing is converted into v. So if I happen to write, let's say if I happen to write between the reference level O and 2, the energy equation between the reference level O and 2. At O the pressure is atmospheric, there is no velocity because larger dia, height is h from the nozzle level, and you don't have anything else, you don't have any losses I neglect, let's say. So at the outlet of the nozzle, this is the nozzle, right, which converts this head into the kinetic energy. So at the outlet of the nozzle the pressure is again atmospheric by rho g because it's a free stream into the atmosphere. Any stream which is open into the atmosphere, the pressure is atmospheric pressure. Height is 0 because it's, and the velocity is v square by 2g. So your pressures get cancelled, v square by 2g. So velocity coming out from the nozzle, or that is the velocity of the fluid that is striking the one of the bucket, is root 2gh. That is, and h is the head present, head available. Okay, so now let's see more about the bucket. How does it moves? Let's take a single bucket. This is the flow. The flow deviates like this after striking. Okay, so this So this is how flow moves. So now let's draw the inlet velocity triangle. So inlet velocity triangle, you have, so the let's compare, let's see this point. This point moves with velocity u, okay, and the absolute velocity is, what is your v? So the velocity of the tip of the blade is, and this point is u, velocity of the blade. The relative velocity of the fluid the relative velocity of the fluid with respect to the plate is also in this direction, Vr1. The resultant of u and Vr1 is your capital V. So this is your inlet velocity. Now at the outlet, let's say this point, either you can take the top. So this is your, so blade angle is expressed in this way. Okay, this is, let's say this is your, this is how it turns. So from the direction of the jet to how much it is, so this is how the blade angle is measured. I mean jet angle is this, it all different terminologies. So let's call this angle to be phi. So your relative velocity is in this way, Vr, okay, and your u is in this way, okay. So the resultant, okay, so let me, u is in this way, so let me draw here. Vr relative velocity is this, your u is not going to change here because everything is happening almost at this bucket level, and the radius change here and here, the radius change are not much, so u is same as the inlet, okay. And then combining this v and u, you have the absolute velocity, which is, okay, I think let me draw outlet at the after inlet, okay. So just hang on. Okay, so at the outlet, if you look at it, that's how the jet enters and this is how the jet goes. So at the outlet, the relative velocity, what an observer will feel if he's on the bucket, you'll feel the fluid is moving like this. So this is Vr, okay. Your u is in this way, and the resultant of Vr and u, that is your absolute velocity, which is in this way. So let me draw it again. This is relative velocity Vr, your u is this way, the resultant of the relative velocity of the fluid with respect to the tip plus the tip velocity, the resultant is the final velocity Vf. So the inlet triangle is u, Vr and V. This is the inlet triangle. The outlet is Vr, which makes angle phi, your u, and your final velocity v1, okay. Or let's write this as v1, this is v2, okay. Okay, so one assumption is, what is the relative component, of velocity does not change. That's an assumption. So relative velocity at the start is Vr is v1 minus u, and that is the relative velocity at the outlet also, okay. Okay, okay, so that is one thing. So now what we understand is the force imparted because of the jet, force imparted on the plate is basically the change in the momentum, right? The force imparted on the plate is change in the momentum, the decrease in the momentum. So mass flow rate, initial momentum in the left direction is v, okay. So how do you, okay, the initial momentum is v1, the velocity is v1 in the direction, so that is the initial momentum minus the final momentum in this direction. So final momentum v2 is in this direction, okay. If I happen to resolve v2, so resolving v2 is nothing but, so if let's say this is Vr, this is u, this is v, the component of V along this is VW and this is Vn. So this VW is towards left. So minus, so this is initial momentum of the fluid, minus the final momentum in the same direction. So final momentum is in the reverse direction, so minus mvw. Okay, how do I now convert these v1s and v2s? So m dot initial velocity minus, so this is plus m dot vw. Now vw is the resultant of v, that I can just treat it as vw is nothing but vr. If you resolve vr, this is phi, so vr cos phi minus u is my resultant horizontal component of the velocity. Now vr, we have assumed that it doesn't change, so m dot, I can write v1 minus u plus vr cos phi, and vr I can write v1 minus u, so entire thing can be written as v1 minus u 1 plus cos phi, because vr can be written as v1 minus u. Okay, so v1 I am just calling the velocity that comes out of the nozzle, so 1 plus cos phi. So this is the force that is imparted. So the torque that comes imparted to the impeller is force into the radius r. Remember, radius is not changing, u's are not changing. This is m dot r v minus u 1 plus cos phi, where phi is that angle. Okay, so phi, remember that phi is, this is the outlet, this is the inlet, this angle is phi. Okay, and this is the torque applied. So mass flow rate I can write rho q r v minus u 1 plus cos phi. So this is the torque, and your power delivered by the fluid will be torque into omega, so that is rho q r omega v minus u by 1 plus cos phi. R omega I can write u, so rho q minus u by 1 plus cos phi. Okay, so this is the power delivered by the fluid. So the power delivered, now we define another term called hydraulic efficiency, which is the power delivered to the turbine by the kinetic energy of the fluid coming out from the nozzle, So power delivered we have just derived rho q u v minus u by 1 plus cos phi, and the kinetic energy is half m dot v1 square, or v square in fact. Okay, so this is 2 rho q u v minus u 1 plus cos phi, and m dot is rho q v square, so this can be rho q gets cancelled, so it is 2 u v minus u 1 plus cos phi by v square. So this is how your hydraulic efficiency, how much portion of the kinetic energy of the fluid you are converting into the power. That's it. Now one thing is, for a given blade angle, like for a given phi, n is maximum when u is v by 2 or 0.5 v. This can be easily derived. I mean, you can just differentiate dn by dv and set it to 0. You will get that when u is v by 2, hydraulic efficiency is maximum. Okay, and for a given other way of looking at this is, if phi is max more, then that means if phi is say 90, so, or let's say phi is 0, so if phi is tends to 0, that means almost the blade angle is 180. I mean, this is the total angle. So this is called the jet angle, the jet deviation angle, and this is phi. This is phi. So this is the jet deviation angle, and that deviation will be 180 if phi is 0. So in that case, the hydraulic efficiency will be maximum. So most of the time, that's why we have a semicircular vane which the jet deviation angle is close to 180. So this cos phi term is 0, and phi is 0, cos phi term comes to 1 and it becomes 4u. So in that case, when phi is 0, in that case the efficiency is 2u. This happens for a semi-circular bucket. So it comes out to be 4u v minus u by v square for semicircular vane. So this is all about hydraulic efficiency. So we have seen the Pelton wheel, power delivered, the Pelton wheel work, the efficiency. So these are the important things in turbines. Thank you.